Okay, hello everyone. We are continuing with Grade 12 Physical Sciences Paper 2 from November 2023. This is the long question section. Previously, we've done the multiple choice section in a separate video and question 2 in a separate video as well. And now we're moving on to question 3. So, question 3, diving straight into it. The relationship between the boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. Curves P, R, and S are obtained. All compounds used are straight chain molecules. Okay, so it's important just to note they give us this piece of information, straight chain molecules. Why is this important? Well, the trends in boiling point can change if you have branches in your molecule. Branches lead to ineffective packing and unequal distribution of intermolecular forces, which can drastically change the trends in boiling points. So they just give us this piece of information, so we know we don't have to worry about that. We can just apply the general expected trends. So that's useful, just to keep that in mind. So they give us a graph. Um, yeah, Next, the first question, define the term boiling point. So there's quite a couple of different ways to define this, but your answers must definitely include uh, two key phrases. The first one is that boiling point always happens at some temperature, right? So your answer definitely has to have temperature. So the boiling point of a molecule is at some temperature. For water, we know at sea level, it's about 100 degrees. For us, a bit above sea level, it's actually a bit below that. So it's the temperature at which the vapor pressure equals the atmospheric pressure. Vapor pressure, okay, that's the next key phrase, equals atmospheric pressure. If I can spell equals atmospheric pressure. So this is why boiling points change depending where you are. If you're closer to sea level, atmospheric pressure is slightly higher, so boiling points are actually at higher temperatures. If you're a bit above sea level, like on a mountain or something, or yeah, then the atmospheric pressure is a bit lower, so it takes less time for vapor pressure to equal atmospheric pressure, and that happens at a lower temperature. So, however you describe your boiling point, you just need to make sure that you talk about temperature, you talk about vapor pressure, and you talk about atmospheric pressure. Those are the key words to get the full marks. All right. Moving on to question 3.2. Write down the conclusion that can be made from curve P. So let's have a look. So curve P starts around 100 degrees with a molecular mass of just below 50, and it ends around 200 degrees, and that compound has a molecular mass above 110. So what we can see is as our molecular mass increases, the boiling point also increases. So that's all you need to say for question 3.2. As molecular mass increases, boiling point increases. That's the conclusion from curve P. So, question 3.3. Explain the answer to question 3.2 in terms of structure of the compounds. So, for this one, the question is basically asking why does the boiling point increase as the compound gets heavier? So, these are all straight chain molecules. So, what we can see is that the molecule is actually getting longer and the boiling point is increasing. So what that leads you to conclude is that a higher molecular weight, so or molecular mass, so increased molecular mass, I'm going to write it as MR for shorthand, means um, a longer molecule, longer molecule. And if we have a longer molecule, it means we have increased intermolecular forces, or IMF for short. So it doesn't matter how you phrase this, you just need to basically get to the point that there's more intermolecular forces with longer molecules, there's more sites for London forces, and if there's more intermolecular forces, well, now we need to relate that. So for the second mark in the question, we need to relate that to boiling point. Basically, well, if intermolecular forces are higher, it means you need more energy to break them. And if you need more energy just means that has to happen at a higher temperature. So that's how you relate. So we can say this leads to increased temperature. So now we can relate the high molecular higher molecular masses to the increase in boiling point following this logic. So you can phrase your answer however you like. You just need to ensure that you include these key things in order to get all the marks. Okay. Question 3 4. Curve R represents the alcohols. Okay. Maybe I'll just write that here so I don't forget. So they tell us R is alcohol. Okay, great. Which homologous series is represented by curve S? Okay, so what have they told us? We have carboxylic acids, primary alcohols, and aldehydes. Um, so if R is alcohols, then what is S? Is basically what the question is saying. So carboxylic acids, if we just remind ourselves, have the functional group C double bond O O H. Alcohols C O H, and aldehydes C double bond O H. So what we can see here is that carboxylic acids and alcohols have got this OH bond, which means they're capable of hydrogen bonding. But aldehydes aren't. The H is bonded to the carbon, not the oxygen. So aldehydes don't have hydrogen bonding, and hydrogen bonding is one of the strongest intermolecular forces. So we would expect aldehydes to have lower boiling points than both alcohols and carboxylic acids, which means S has got to be the aldehydes. It's the only one that doesn't have hydrogen bonding, so it should have lower boiling points because it has weaker intermolecular forces. So that answers question 342. Explain the answer to question 341 referring to the strength of intermolecular forces. So I've kind of already done that. I guess to answer 341, you just have to say aldehyde, and then to answer 342, you can then elaborate and explain about the different intermolecular forces. To get the full marks, you don't have to go into detail of hydrogen bonding. You can just say difference in strength of intermolecular forces. So you should just know aldehydes have weaker intermolecular forces. So we might as well just complete it because now we know P is carboxylic acid, carboxylic acids. But yeah, so that's 342. Aldehydes have weaker intermolecular forces. Done. For curve R, write down the molecular mass of the compound with the boiling point of 97 degrees Celsius. So curve R, that's our alcohols. 97 is 97 is this point here. So following this point down, you could use your ruler for this. And then counting, we have 1, 2, 3, 4, 5. So we have 10 boxes in between 50 and 70. That means each box represents 4 degrees. And this is coming around box number 5. So 5 times 4. No. This is 60, basically. Each box represents 2 degrees, not 4. So 5 times 2 is 10. 50 plus 10 gives us 60. So we know that for curve R, the compound with a molecular mass of, or boiling point rather, of 97 degrees has a molecular mass of 60. All right. So we can just write this in here, 60. Mm, so yeah, the answer to 351 is just 60 degrees, 60 grams per mole. Sorry. Then it says, for curve R, write down the IUPAC name of the compound in question for 351. All right. So here we gotta do, we gotta kind of break it down a bit. We know it's an alcohol. So our alcohol is gonna have some carbons. It's gonna have mm, 2n plus 1 and then OH at the end. So this is basically the equation that we're going to use. Must remember carbon has a molecular mass of around 12. Hydrogen, for simplicity, we'll just keep it at 1. It's not exactly 1. Same for oxygen, we'll just keep it at 16. It's not exactly 16, but this is good enough to get us through this question. And then our total molecular mass for this one is 60. So you can just try different size compounds. Um, yeah, that's pretty much a way that you'll always get your answer. But what you can do as well is just say, okay, we either way we're always gonna have an OH group that's 17. So let's subtract 17 from 60. So 60 minus 17 is gonna give us 43. So we're left with 43. And how many carbons can we fit into that? Actually, only 3. So, yeah, because you get to 36. So you can just say, because hydrogen is such a small molecule, it only has a molecular mass of 1. You just got to fit as many carbons, and then usually the difference will balance out the hydrogens. So we can just try 3. So this is a good way to like try and get a, instead of just trying starting from methanol, ethanol, propanol, butanol, and like just going through it. You can just do it this way and say 12 into 43, you get about 36, right? So 3. So we can just guess propanol and then check. So we're guessing propanol, C3, H therefore becomes 7, OH. And if you check this, we know this is 17, this is 7, and this is 36. So 36 plus 7 plus 17 adds up to 60. Um, so this is a much quicker way of arriving at the answer. So we know that propanol is definitely the one with a molecular mass of 60. So the IUPAC name is okay. So they want the IUPAC name, so you have to give a very specific name, not just propanol. Um, It's a primary alcohol, so because it's primary, we know that the OH group is at the end of the molecule. So if we draw it, propanol, 3 carbons, OH, populate the hydrogens. So this is propanol. So the IUPAC name would be 1-propanol, or as we discussed before, you can go propan, propan dash 1, all, or however you prefer to write it. Yeah, so that would be the IUPAC name. You have to include the 1 because by including the one, that's how you distinguish it as a primary alcohol. If you just say propanol, the OH group could be in the middle of the molecule, and that could be like a secondary alcohol, not a primary. So that's the trick to question 352. Finally, question 36, the last question for question 3. Two compounds A and B used in the investigation um, have a molecular mass of 74 grams per mole. A has a boiling point of 118 and B of 142. Explain the difference in these boiling points by referring to the structures of these compounds. So 74 grams per mole, we can come here to our graph. We just want to see which molecules they're referring to. So again, use your ruler for this. 74 is about here. And we can see that the compounds A and B, one is an alcohol. So one is an alcohol and one is a carboxylic acid, because there's no point lining up with our line for the aldehydes. So this helps us. We already know, okay, they're referring to a carboxylic acid and an alcohol. And then they tell us that A has a boiling point of 118 and B of 142. So A, with the lower boiling point, is definitely an alcohol. So, okay, now we have some information. So A is an alcohol, and B with the higher boiling point is a carboxylic acid. Okay, so the question was asking us explain the difference of the boiling point by referring to the structures. So you basically have to talk about the different intermolecular forces available to these classes of molecules. You don't have to work out the exact molecule and then talk about that one in particular. You can just talk about alcohols versus carboxylic acids in general. So so first of all, carboxylic acids, which is B, in addition to London forces, also have dipole-dipole forces, and they have two sites for hydrogen bonding. So this is a key difference, because the functional group is something like this, and there's lone pairs on this oxygen and lone pairs on this oxygen as well. There's two sites for hydrogen bonding to occur, unlike in an alcohol where there's only one oxygen. So there's only one site for hydrogen bonding to occur. So this is like one big difference between the two. Um, Alcohols do have London forces and dipole-dipole forces as well, but they only have one hydrogen bonding site between the molecules. So that's how you reach the conclusion that intermolecular forces in carboxylic acids are stronger and more energy is needed to overcome them, hence the higher boiling point. And that answers the question. So with that, that concludes question 3.